Welcome everyone to our YouTube channel, Niseem. This is a broadcast that's targeting the Arabic audience and mostly the Middle East. Today we have a very special guest. We have Leonard Susskind. I'm very happy to have you in the show.
Thank you.
Leonard is a professor of theoretical physics at Stanford University. His research interests include string theory, quantum field theory, and quantum cosmology. He is a member of the National Academy of Science of the USA and the American Academy of Art and Science, and a distinguished professor at the Korea Institute of Advanced Study. He is widely considered as one of the fathers of string theory and independently introduced the idea that particles could be state of excitation of relativistic string. He was the first to introduce the idea of string theory landscape in 2003. One more time, I'm really happy to have you on the show.
Thank you.
Physics is me, you, and us. Why do we study it? How can we understand quantum mechanics, relativity, the Big Bang Theory, and our universe? All of this and more are discussed by Dr. Niseem Magdy at the YouTube channel Niseem.
When we first start, I think every physicist is asking himself this question. We do physics because we love knowledge, we love to learn. But the question to Leonard, what's really motivate you in physics? What you try to get out of your research?
Well, I think it's just simple curiosity. And it's a little more than curiosity. It's the fun of the exploration. It's puzzle solving. Puzzle solving is always rewarding. Of course, it's also frustrating. You spend a lot of time not knowing what the answer is, and then you know the answer, and you're excited for a small amount of time, and then you go on to the next puzzle. But basically curiosity. Curiosity, how the world works, what are the connections between the different kinds of theories that describe different phenomena? Are they consistent with each other? Is the world the way it is because of deep mathematical principles? What are those deep mathematical principles? And quite frankly, I can't really think of anything else I ever really wanted to do. So I don't spend a lot of time thinking, why am I doing this? I just do it because I love it.
I can relate pretty much. Yeah, I think that's
sure.
Most of us usually, when you just try to go to college, you think about what you would like to study, and then everybody just find his own spark. That's this is what I want to do. And I think so basically curiosity is your biggest motivation.
Yeah,
that's really great. So actually, I followed closely your online courses at Stanford. I will say this is one of the best for the physics education.
Thank you.
Very deep knowledge. Usually I really enjoy it. And one of the courses that I really enjoyed was the quantum mechanics. And my usual question that I usually get from my audience, so we try to, as I would say, we moved from the Middle East, Arabian countries. I'm from Egypt originally. Now I'm doing my second postdoc at Stony Brook University, United States. And we try to reflect back about the main questions we get usually from people in this region. And I think one of the questions is, what you think, in your point of view, is the biggest mystery of quantum mechanics? What's the most mysterious thing in quantum mechanics to Leonard?
Well, there are so many of them. It's hard to focus on one particular one. And sometimes questions are so confusing and so, what shall I say, confusing. That's the only word I can think of. That it's really hard to tell if they're even questions, if they're really good questions or not. Questions like consciousness. What makes consciousness? That's not a quantum mechanical question, I don't think. But still, it's very hard to imagine exactly what an answer would be. Quantum mechanics is very confusing. It has this strange many world aspects to it. Quantum mechanics is statistical, and because it's statistical, it means that probabilities branch, that possibilities branch.
Mhm.
We're sitting here now, and every time I make a tiny little decision about what to say, according to quantum mechanics, in some sense, the world, or at least the wave function, branches and branches into branches, most of which probably sound pretty much the same way we're hearing it now. But with some small probability, I say blah, 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 or I say kick, kick, kick. And those branches, do they constitute part of reality? Do they constitute part of the world? Or are they just mathematical fictions and the real thing is what we think we perceive? So there's many world aspects of quantum mechanics. The way probabilities, not just probabilities, but the way that possibilities branch and create many, many worlds of different possibilities. This is extremely confusing. We don't really use quantum mechanics that way. We make predictions and we predict the outcome, and the outcome is statistical. And in a laboratory, we don't worry very much about all these questions, but they're there. And another way to say it is it's very hard to understand in quantum mechanics what is real, what is reality. Does reality really mean anything in this world where all there are probabilities? So that's a very deep question. I don't know that it really will ever be answered. So if we came to questions now, which I suspect will be answered,
Okay.
well, there's a lot of them. Can a quantum computer be built? Or is there some deep obstruction that we haven't figured out yet? How does quantum mechanics connect together? There's, of course, how quantum mechanics connects together with gravity. I haven't included that because I think we're making definite progress on it now.
Yes.
So I think that is going to be, at least in part, solved. But the question about how quantum mechanics, together with gravity, fit into the cosmological world is still obscure. The ideas that we have for how quantum mechanics and gravity fit together never quite refer to the world as we know it, never quite refer to the expanding universe, never quite refer to the accelerating universe. They're always models which contain gravity, which contain quantum mechanics, but which are different in the real world. So how quantum mechanics and gravity fit together with the real world, meaning the world that astronomers and cosmologists and experimental physicists actually perceive in their experiments, we don't know yet. And we especially don't know how all of this fancy new quantum gravity stuff fits together with elementary particle physics. We suspect it does.
That's the expectation,
That's the expectation.
Yeah.
But do we have any direct good ideas about how to use the ideas of quantum gravity to solve the puzzles of particle physics? Of course, there are some people who do think they have a good idea. And maybe they do. I'm thinking about string theorists particularly.
Yeah, it depends if you can test them in the
String
lab.
theorist has his own different version of it.
I think it will depend if we can test them in the lab and if we can.
Yeah.
I'm working here. Part of my group is working in CMS at CERN. The other part is here in United States in RIC. And then I think we still, on the energies we use, the part of tera electron volt or giga electron volt, I think we still, we need some time until we reach that level. But since you mentioned the quantum computing, usually the expression of quantum information is mentioned, and I think they're I couldn't find an easy way to explain what's a quantum information mean to a physicist.
Yeah.
So if you can help me on that, this would be great. So,
well, the first question is, what does information ever mean? And information has to do with distinctions between There's a piece of information in knowing that a particle is an electron versus a muon.
Mhm.
That's a piece of information.
Yes.
And what is information there? It has to do with distinctions between different possibilities. And that's really all that information is. The yes-no questions that you need to answer in order to specify whatever it is you want to know. If you want to know the precise state of the universe at this time right now, there's a very large number of yes-no questions that you would have to answer. Is there a particle over here? Or is there a particle over here? Or is there a particle over here? How many such questions are there? Well, actually, we know the answer. The answer is 10 to the 123, I think. And don't ask me where that came from. You can ask me later.
Okay.
But we actually, that's a very large number. 10 to, it's a 1 with 123 zeros after it. Is it 123 or is it 120? I don't remember. But it's a very, very large number of pieces of information that you would need to know if you wanted to be able to predict, quantum mechanically predict everything that will take place later.
Yeah.
So it's all the distinctions that you need in order to predict the future, let's say, insofar as the theory allows you to predict the future. Now, of course, we don't need to be talking about the whole universe.
Mm-hmm.
We could be talking about some small part of the universe and ask how many pieces of information do we need to describe some small part. And fortunately, that's typically less. If we have 3 particles in a box, how many pieces of information do we need to know the future of the box? Well, a few, a handful.
The interaction, what will stay, what will go out, how it goes, how to describe that old system precisely.
Yeah. So that's all information is. Now, quantum information, well, it's what you need to know quantum mechanically to specify the precise state of a system. And it's a little different than just yes/no questions, but basically the same idea.
So can we say like quantum numbers is quantum information? So a part of that.
Well, we just call it quantum information, but in order to be more exact about it, I would have to give you a course on quantum mechanics, which you can go in my book and read, or on my online lectures and watch.
Which I will encourage everybody. I think I was just watching most of this course again. I think it's right.
But there's some first approximation. It's just basically all of the yes/no questions that you need to answer to specify a system or a set of objects with precision, enough precision to be able to predict the future.
So actually, a transition to my I think our main target. In my reading about quantum, I'll say first general relativity. I think we land on that general relativity can describe the distortion in space-time based on the existence of the matter or energy or mass and energy. However, I would say the theory fails in 2 places or in 2 situations. One of them is the singularity, Big Bang singularity, and the black hole singularity. And so what do you think about that? Like, is that the reason why we need a quantum gravity theory?
Yes. Well, it's not just the singularities. It's more than that. We don't, for example, even if we just ignore the question of the singularity, we say, okay, in the past, some event happened, but we don't try to understand that event exactly. We go back not quite that far. We go back to some time 3 minutes after the Big Bang. Steven Weinberg likes to think about 3 minutes after the Big Bang. Okay. At 3 minutes after the Big Bang, there's no question of a singularity. But there is some initial state or some state at that time which we can try to follow forward from there. That doesn't involve the singularity, but we still don't have the tools, either the quantum mechanical tools, especially the quantum mechanical tools, to follow the evolution of the universe past that point. We don't know the rules, the quantum mechanical rules. This is so far the application of quantum mechanics and quantum gravity to the real world cosmology is very much in its infancy. I would tell you, if I wanted to use the words that would make sense to some of my colleagues, we have a deep understanding of quantum gravity in a kind of space-time that's called anti-de Sitter space.
Okay.
Whatever, it doesn't matter what it is.
Yeah.
It's a kind of space-time that amends itself to analysis rather well.
Mhm.
We don't live in a world of anti-de Sitter space. We live in a world that's called de Sitter space without the anti.
Mhm.
Very different kind of space-time, very different geometric properties. One of them grows exponentially. That's the de Sitter space that we live in.
Wow.
The other one has totally different properties. And the one that we understand deeply from the quantum mechanics and gravity point of view is the wrong one.
Okay.
Right.
Wow.
So the other one, we barely understand at all. So there's a great deal to unravel, more than unravel, and all of the progress that's been made. And, the physicists that I deal with and that I interact with, many of them young, some of them not so young, are very proud of the advances that have been made in the last 20 years. Very proud of it. But they are talking about the wrong space-time.
Oh,
So
wow. Yeah.
they've understood something. They've understood something deep. What they've understood is that quantum mechanics and gravity can fit together. They can fit together. They have an example. They have an existence proof of a world where quantum mechanics and gravity fit together correctly, precisely, rigorously, almost rigorously. And that's not a small achievement. It's a big achievement to demonstrate the consistency of quantum mechanics and gravity. But then the next step is to demonstrate that consistency in a context which is more like our own universe. And that has yet to be done.
Wow. That just tells us that there are a lot of work to be done in
Yes,
in
there
the
is.
real world. Yeah. So actually, that takes us to I would say one of the main points for our interview today, which is the string theory. And according to my reading, I used to read since it's out of my field about the string theory, and then I will say it was maybe to me a little surprising to know that the idea originally was developed to describe the strong interaction
Yes.
before the QCD come, or the quantum chromodynamics, which the theory described the strong interactions. So that's precisely what I'm working on. I'm working on the quantum plasma, which is strong interacting system. And I think it was Vinciano when he tried to use this idea of string as a replacement for the current blown.
Well, Veneziano did not think about strings. He had a mathematical formula.
Oh.
He had a mathematical formula for scattering amplitude. You know what a scattering amplitude is. Yes. And he had a mathematical formula which was a function of the momentum of the incoming particles and the outgoing particles. And it was a famous formula. It was called the Veneziano amplitude.
Mm-hmm.
But it was just a mathematical formula. It had two gamma functions in the numerator and one gamma function in the denominator.
Okay.
And it had a lot of interesting mathematical properties. Very interesting. Neither Veneziano nor anybody else knew what the underlying physics of it was. To them, it was just a mathematical formula. It was Nambu and myself who realized that it was describing the scattering of strings. Up until that point, the word string didn't appear in physics. If it did, it probably had to do with somebody's mathematical study of violin strings or something.
No, yeah, I was reading about it, and I think that was maybe the one part that was not getting straight. Yeah, what I observed in the book, they was putting the formula, as you just said, the Vinciano amplitude, and they was saying, okay, the guy was trying to say how the quarks will interact together, what's sticking them together, and he was putting that as sort of substitute for it, and then of course later we know that something else is doing this, with the quantum chromodynamics. But I think as you just mentioned, you guys picked that at least the from there, but at that time it was not a string yet. It was not called even a string yet.
Yeah, now quantum chromodynamics came along. It was a quantum field theory, but as it turned out, quantum chromodynamics described strings. It was a mathematical field theory that was describing string-like excitations. So the string idea for hadrons, for strongly interacting particles, came together with the quantum chromodynamics ideas, and they turned out to be the same. We now know that protons, neutrons, mesons really are string-like excitations. They can be vibrated. They can be...
It's a field excitation, as I understand.
Well, it's a field excitation, but more than that, it's an object. It's an actual object which behaves like a string.
Yes.
An electron does not behave like a string, or a photon does not. You can't excite an electron. You can't cause the internal structure of the electron to vibrate. Not in the laboratory, you can't. At one time, it was thought that you could excite the internal structure of an electron and it would become a muon. That a muon was a vibrating internal vibration of the electron. That, of course, turned out not to be true.
Okay.
But
cool idea still.
But mesons and protons and neutrons do have vibrational excitations. You can take, or even rotational excitations. You can take a proton, and if you hit it just the right way, you can start it spinning with a higher angular momentum. You can cause its energy to increase, its mass to increase. The excitations have different names. The excitation of a proton is called a delta 3/2 or something. I don't even remember anymore. But those are protons which are vibrating. Or spinning.
Yeah, I can imagine that. We had the whole program called the proton spin. This try to study the internal structure from the...
Right. The proton has a spin, but it also has an internal structure. It's made out of things.
Yes.
Those things, when they're excited, behave like, for example, a meson. A meson behaves like two quarks connected with a string.
Yeah, I mean, just for our audience, a meson is a particle that contains two quarks, and then another barrier will be a particle.
Well, it contains two quarks, or a quark and an anti-quark, but there is also energy stored in the string between them. So you can take those two quarks. Let's see, take those two quarks. Here they are, and you can hit one of them, and it will fly. They'll fly apart, but then they'll come back together again. Vibrate.
That's like,
and that's the string. So string theory really was the right theory of hadrons.
Yeah. Based on what I learned, which I do all the day, mostly, I agree that what we think, what we learn. So you guys, I think, picked the idea, you evolve it, and I think originally, according to my reading, the first trial or the first string theory was in 26 dimension originally.
Well, the first one, it was realized only a little bit later that it only made precise mathematical sense as a pure mathematical structure in 26 dimensions. That was, well, I don't know, a year or two after the original proposal of string theory. That was not by me, that was by somebody else.
But usually that's a requirement for the theory to be stable, meaning no violations. It works in the way we expect it to work.
It's required for it to be stable. It's required for it to be unitary. It's required for it to be relativistically invariant. It just has to be right.
Yeah, and then I think
which is, of course, was a terrible thing. Nobody wanted to be thinking about 26 dimensions.
Yeah, when we start, when we speak, okay, we can have 3 at a time. That's what we can understand. Then we're speaking about like 26, and then I think after realizing or making some modification in the theory, we went down to now the M theory about speaking about 11 dimension, the M theory, which actually I had a question for you that seemed like no one knows what it is. What's M stand for? I think.
Well, I don't know what Witten meant when he put an M, and I've asked him, many people have asked him, and he says he didn't mean anything. He just called it M theory. Later on, one version of it or one interpretation of it was in terms of matrix quantum mechanics. And so it started to be called M for matrix.
Okay, so they tried to make sense of it after it had been
there
already.
There was a string theory kind of version of it, which was based on the quantum mechanics of matrix degrees of freedom. That was, it's called BFSS matrix theory. Oh. And that could be an interpretation. Other people said it meant mother theory, meaning the mother of all theories.
Mother of all theories, yeah.
I remember there were other words that people speculated that Witten might have meant. And when he was asked, he said, I didn't mean anything.
Yeah, it's like he wrote it and then everybody had to make sense why M theory. It's like, it's a little funny because I was looking online and it seemed like everybody has his own interpretation why it's an M theory.
Obviously it's not.
And I couldn't find his word outside. It's like, okay, so I thought either he just decided it's an M theory and then everybody after that come up with some interpretation.
He probably meant something, but he's not telling.
Okay, that's good to know. So one thing here, so what is the main things that the string theory solve for general relativity? Like, so we don't have singularities anymore in the theory.
Let's say it again.
Like so now string theory doesn't have any singularities anymore. It get rid of that.
Well, no, I don't. Well, I'm not sure that's correct. It depends on the kind of singularities you're talking about. It is true that the Feynman diagrams of the string theory don't have infinities.
Okay.
That if you think of string theory as a theory of a kind of generalized kind of system of Feynman diagrams, where the Feynman diagrams of gravity are infinite. They have infinities all over the place. They're not renormalizable. The theory just doesn't seem to want to make good mathematical sense. The corresponding things in string theory seem to be finite, and they seem to be well-defined. They seem to have good mathematical properties. So,
so how, maybe a question out of the topic a little bit. So how can one imagine the let's call it the early universe in the string theory, or it does not answer that questions?
The early universe. Well, what I tried to tell you before is that there really is no proper either string theoretic or quantum gravity understanding of the Big Bang. I think that has yet to be answered. I could try to make up stuff, but I would be fooling myself. And I would be fooling you if I tried to make up some grand scenario to tell you how string theory was describing the early universe.
I know you're not that person, so that's why I asked.
No, I'm not that person. Yeah. And as I said, the things that string theory have done and have accomplished are a kind of mathematical consistency of gravity and quantum mechanics. They fit together nicely, but in a situation which is just not the kind of universe we live in. And in particular, it doesn't have a Big Bang.
Yep.
So there we are. We've spent a lot of time in the wrong world, but everybody knew that. The idea, and I think it's still a correct idea, is to unravel and completely understand that model world, which is not our world, learn all the lessons that we can from it, and then try to put them together and see what they imply for something more like the real world. And that's only beginning now. That's very much in its infancy.
Okay.
There are some thoughts about how inflation works in string theory, but for every thought about how inflation works in string theory, there is some other thought that inflation will not fit together with string theory, so it's not clear.
Okay, so we can say that we have the first framework that could hopefully drive us in future to have more understanding of our universe as it is right now. So
yeah,
that's really great. So even with that current universe of string theory, I have maybe two questions remain. One of them related to the what we call brains. It's like brain is like, I would say, when we take the brain on one dimension, it is a string. But yes. I don't understand much about that. So if you want to elaborate.
Well, that's right. I mean, a brain in one-dimensional brain. Incidentally, it's not BRAIN, not like this kind of brain.
Yeah.
BRANE, like a membrane.
Yeah, membrane. Yeah.
Right. A membrane is a two-dimensional brain.
Mm-hmm.
A membrane is a two-brain. It has two dimensions. A one brain, that's a one-dimensional thing, that's a string.
Mm-hmm.
A three-dimensional brain, a three-brain is a solid chunk of material in three-dimensional space, and so forth. One of the discoveries in the context of this not quite real-world kind of string theory was that string theories always have membranes as excitations. They always contain mathematically and in principle things that could be produced, for example, in very high energy collisions. Mm-hmm. They could be produced, really produced. Membranes, like a balloon. A balloon would be a membrane. They always have strings. So that was one of the lessons. And I think most of us expect that although we're going to be going to a different kind of world when we study the real world, the lessons of string theory will inform us that very likely there will exist in that world brains, higher dimensional brains. What do we do with them? Well, one interesting theory is that the universe is filled with what are called cosmic brains, cosmic strings they're usually called, but they are brains. And that at one time it was even thought that they might replace dark energy. That did not turn out to be the case. Mm-hmm. But it is still very possible that the universe is filled with a network of cosmic brains, and that would be detectable in astronomical studies. So the lessons that we learned from string theory hopefully will translate into real world physics. But that's a way down the line. It's not happened yet.
That's great. I think our technology is getting better. We're getting better in technology, building machines.
Much better.
Who knows? Maybe in future we'll have better handling on that. I'm really, really very thankful for you, Leonard, for being around today. And I will say at the end, the floor is yours. If you would like to give some advice for the Arabian physics students and the non-physics audience, the people that don't study physics. So if you have any advice, last word you would like to introduce to them, the floor is yours.
Do I have any advice? Well, I have some advice for my young physics colleagues, graduate students, and so forth. And my first piece of advice is when you get burned out and when you get tired and when you can't make any progress, do something different for a while. Go skiing. Go play tennis. Do something else. And don't worry, because if you're really built to do physics, the curiosity and the fun of it will come back. So take a break. That's one piece. That's something I always tell students.
I fully agree.
Don't get crazy if you're having trouble making progress. Just go do something else. Go to the movies. I don't know, and just wait until the urge comes back. What advice do I have for what advice do I have for the non-physicist who is trying to keep track of things in physics?
Yep.
Well, don't believe the media when every other day they announce some revolution in science.
That's a great advice. That's really good advice.
The media makes its living, its financial living, by keeping you interested. And the way to keep you interested is by telling you every other day that there's been some incredible advance, but there isn't an advance every other day.
I fully agree. You know, that's one of the reasons why I made that YouTube channel. It's all of this, I will say, non-accurate. I will say that's non-accurate claims made by the media. And I think it's now we have a different kind of media that we can introduce by having people like you.
There's lots of kind of media, and even the mainstream media. There's some very good stuff. I mean,
yes,
the New York Times isn't great on science, or at least our kind of science, but at least has at least one journalist who is very good, Dennis Overby. He's extremely good, and but for everyone like him out there, there are dozens who are writing for less prestigious journals and so forth. And it comes across my screen, since I tend to look at these science things.
Sometimes fun to look at.
It's always on my screen. And every other day, I would look up now for you, but we don't really have time. But I'll bet you today that there's some great new discovery, which is not a real discovery, but which is being announced in order to get you to click on the tab. And what do you get when you click on the tab? You get A, a story which is an old story, B, a story which no serious scientist necessarily believes in, and 3, you get advertisements.
Yep. Which is what they care about. So hopefully we introduce something different.
So take with a grain of salt every time you hear there's been some great new advance, because mostly it's not true.
I fully agree. And finally, I really, really thank you for today's interview. I hope it's not the last. I hope you have a very, very wonderful day, and
you too.
Always be shining on us with all of the knowledge that you have. Okay. Thank you so much.
Okay.
I wish you a great day. Thank you.
Thank you too. Bye-bye.
Bye-bye.